Welcome, this is Mr. Dahlstrom going over the book homework, or at least some specific book homework for this chapter of pre-AP Physics. It's chapter 6, Work and Energy, page 220, 60 through 71. We're going to talk about some of these conceptual ones, talk a little bit about some of these math ones here, and then wrap it up. Shouldn't be too long here. A lot of the work conceptual problems here, if we start looking at them closer, is that they are, let me refocus this right here, is talking about, do you understand if work is being done, whether it's positive, whether it's negative, or no work is being done. So before we get into answering some of those conceptual questions, let's just do a little bit of review here and showing sort of what the work is equal to FD cosine theta. And we have, if we have an object here, let's say the direction of travel or velocity is this way here, we can have a force at really, excuse me, any angle. So this would be our force, and there would be a theta. So what the theta represents is, that's actually one of the questions here. What does the theta mean in FD cosine theta? It is the angle between the force and the direction of travel. So this is direction of motion or travel. So that's what the theta means. The F is the applied force, so the overall applied force, and D here is the distance, which is the distance that is moved. So in calculating, or that, let's go ahead and look here. It says only, a friend makes this statement, only the component of force perpendicular to the direction of motion does work. This is a false statement. So you're saying of this. So let me redraw this again, and we'll kind of show how we did this before, where we had some applied force here, and then we had components of these vectors. So I have a red and I have a blue. So in this example, we'll have blue be our horizontal component of the force, Fx, and then we'll have a red be the vertical, Fy. It should look familiar here, where this is theta. And so what it says back over here, it says a friend makes the statement that only the component of the force perpendicular to the direction of motion does work. This is incorrect. Only the force that is parallel to the direction of travel. If we're moving in this direction, then it is only F of x here that is doing work on them. What does it mean doing work? We're putting positive energy into a system. F of x is the only force here, or the only component of the force that's actually causing this object to accelerate or speed up. F of y is not acting on this. So basically, F of x is causing an acceleration, where F of y does not have any kind of acceleration. So only the parallel component causes any type of work. Whether it's positive work, it could also be negative work, which I'll show you here, where it's basically you're still traveling in this direction there, but let's say we have it's facing now in this direction. We have F of x, this is this way. Sorry, I'm moving my camera here. F of x is this way, and F of y, which is this way. F of y still is not doing any work because it is not parallel to the direction of travel. F of x here would actually be doing negative work because it's acting against the direction of travel. It is taking energy out of the system. Friction would be an example of F of x here, while up here this would be positive work. Now, in order to get no work, that means that our, over here in this example, to do no work, that means that our force has to be, let's say we're still moving to the right here, the force would have to be perpendicular. So whether a force like this or a force like this one or this one, they're neither doing work because they're not acting in the direction of travel, or sorry, they're not necessarily acting in the direction of travel, but this angle here, this theta, is equal to 90 degrees or 270, and if we plug cosine, force times distance times cosine of 90 is 0, so no work is being done. So with that out of the way, let's look back at some of these questions here. So this is a false statement here. It is only the parallel component that causes work to be done. And the equation, what does this mean? We talked about the angle is the angle between the force and the velocity, or the direction of travel. The general equation of work is work equals FD cosine theta. For what angle is the work F times D, and for what angle is the work negative F times D. So we talked about it in terms of this. For you to be doing negative work, let's take this out of a system here. We'll say that here we have the force this way, and we're moving in this direction. And the second scenario, we're still moving in this direction, but now the force is over here. So in this scenario here, because the force is, if we want to draw it like that, the angle here is 0 between that, so that means it's FD cosine 0, and that equals 1, so it's work equals force times distance. Whereas this one down here is work equals FD cosine of 90, 180. And cosine of 180 goes to -1, so we have work equals negative force times distance. So negative work, like we talked about here in terms of f of x, it's acting in the opposite direction. The angle is 180 degrees from the direction of travel, so that's what would give you a negative work. Okay, 63, your favorite uncle makes this statement. What kind of uncle would make that? Probably me. I have 2 nieces. They're 5 and 6, and they're going to probably have an uncle asking them these kind of questions as they get older. A force that is always perpendicular to the velocity of a particle does no work on the particle. That is a true statement, which is what we talked about. If it is perpendicular to the direction of travel, no work is being done. So in this case, work equals 0. So that is go back here, that is a true statement. A force that is always perpendicular to the velocity of a particle does no work on the particle. I said that is a true statement because the cosine of 90 or cosine of 270 is 0, therefore the work is 0. Next one, triple choice, so 64, 65, and 66. Let's check the time here. Okay, we're good. The International Space Station orbits the Earth in approximately a circular orbit at a height of 375 kilometers above the Earth's surface. In one complete orbit, is the work done by Earth's gravity on the space station positive, negative, or 0? So let's go ahead and draw a little picture here. So if we say that this is the Earth, and we have a circular orbit, that's close enough. If we look at different points around here where the space station could be, draw it as a circle just to simplify it here. When we talked about circular motion before, we used a certain term for this velocity. We called this velocity a tangential velocity. Because why? Because it's tangent to the circle. So let me actually draw this with this. So my velocity is always tangent. At any point, it's been Newton's first law is trying to travel in a straight line, but something's causing it to go away from that line. So that's your velocity, right? Your velocity. And if we look at it at any point, let's look at it up here at this point. We have there, and it's moving this way there. Okay. Our gravity is always facing towards the center, so our gravity here is facing this way. There's gravity, 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 and gravity. And this is another hitter here. It's trying to say, is there any work being done by gravity? The answer would be no, because this is a perpendicular angle, so no work is done by gravity. Okay, so that's basically, if it was an elliptical orbit, then you might be able to say that some work is being done because your velocity and your gravity would not always be perpendicular to each other. But for a circular orbit, we can say no work is done by gravity. Okay, back to the book. 65 and 66 are all referring to this pendulum right here. So swinging back and forth. A pendulum bob swings from point A to point B along the circular arc indicated in figure 6.10. Is the work done on the bob by gravity positive, negative, or 0? Okay, so in this scenario of A to B, I'm going to break the rule here and draw in my book. So at any point, this is the velocity. Okay. And then we have the force of gravity, which is straight down. And so there's 2 ways we can think about this. If we have to realize that this is sort of our axis there, and this is our axis there. There's a component of the force of gravity that is helping or aiding the velocity. Basically, is another way of thinking about it is the work being done positive, negative, or zero. If it's speeding it up, then positive work is being done. It's how you're introducing energy into the system. So it was at here, and it's converting into kinetic energy, and that is the work that's being done. Like I said, it's positive in that case. We can also look at it in a little more complex way. If we look at this bobber here, and we think about it like our components. We have our velocity. Let's say orange is the velocity at that point. We remember this. We have the force of gravity that's there. And then we have two components. We have this component. This should look familiar. We did this for inclined planes. And then we have that component right there. So the y component of gravity is not doing any work. Why? Because it's perpendicular to the velocity, but the fg of x here is parallel, so this is doing positive work on there because it's in the same exact direction, whereas over here, zero work is being done. So they're just asking, is gravity doing any work on it? It is. And is that positive, negative, or zero? It's positive, because it's in the same direction of velocity, but it may be just another easier way of thinking about it is it helping it speed up? Yes. There's the idea of the work kinetic energy theorem, where work equals the change in kinetic energy. It's increasing its kinetic energy. Work is being done on that, and so it is positive work. Positive work, increase in kinetic energy. Negative work, decrease in kinetic energy. So, and then now we'll be looking at the string. Is the work done on the bob by the string positive, negative, or zero? So now we're looking at the work being done by the string. And here we look back at the string and saying, okay, what's the force on the string? This is the force due from the string. There. We would call that tension. And in this case, if we look at it, it is perpendicular, so it's not doing any work at all here. So the tension is doing no work. The force of gravity in the y direction, air quotes, y direction, is doing the work. Like I said, that's define it sort of like that. So tension, the string is doing no work because it's perpendicular. Okay, that answers that one. So that's from A to B. At point B here, I don't think it asks about that, but at point B, there would be no work due to gravity because your velocity would be completely sideways. Just commit to just drawing in the book. And the force of gravity would be straight down like that. And so because that is a perpendicular angle, it is doing no work. 66 we're looking at now, it's going back up here. And so we can kind of draw it. I'll draw it again there. Where's that? Okay, direct this. So now it's over here. And we have our different forces. We have our tension. We have the velocity. The velocity is moving. It's still moving in this direction as it goes there, or at that point. That's the direction before it changes which way it's going. The color we used, we have, this is F, G, or sorry. There's the gravity. There's Fg of y. And here is Fg of x. And so the question is the work done on the bob, that's what the bob is, the little circle, is it by gravity, is it positive, negative, or zero? So once again, it's parallel, but the difference between this and here the force of gravity in the x direction was parallel with velocity, so positive work is done. Here, the force of gravity in the x direction is in the opposite direction as the velocity, so negative work is being done. Also makes sense because it's slowing down, like if you're on a swing, as it goes up, you're starting to slow down. Gravity is doing work on you to slow you down. In this case, it's negative work because it's in the opposite direction. Once again, the component in the y direction is not doing any work because it's perpendicular, and the string is doing no work. So it's just gravity back and forth. That's the only thing that's affecting the swinging of the bob. Okay, so in short, when it's going down here, there's a component of it that's speeding it up, causing positive work to be done. Here, no work is being done by anything because all the forces are perpendicular. As it starts making its way up to this point up here, the force of gravity is now trying to slow it down, therefore negative work is done. So positive work, 0, negative work, and then it changes direction. It would be positive work, 0, negative work, and then back and forth. That wraps up the conceptual problems. The remaining problems that you complete and turn in are 67 through 71. Just talk real briefly about this. Some of the questions there is that they're having you calculate work in terms of things. So work, once again, could be FD and cosine theta. Some of these, if you're just lifting it straight up or you're moving completely side to side, then you don't have to include cosine theta. It's really only when they invoke an angle here. So we can kind of simplify this by saying work is equal to force times distance. But remember, if you're not given, or not remember, there's a way to calculate this. What if they don't give you the weight of the object? You use this one if they give you the weight or the force. Basically, if they give you the value in newtons, use that one. But if we did not know what the weight was, instead if they gave us the mass, we would have to calculate m times g times d. That will be used if they give us the mass here in kilograms. So a good example of that is the very first one here in 67. It says a dog lifts a 0.75 kilogram bone straight up through a distance of 0.11 meters. How much work was done by the dog? So we have a distance that's given here, 0.11, but we have a mass, so we'd have to do 0.75 times 9.81 times 0.11 to give us work done there. So that's what we calculated. The other ones I wanted to talk about, you can fill those out. By the way, the unit for work is the same as energy. If I can write it in there, is going to be J for joules. And it makes sense if work is how you put energy in or take energy out, it would make sense that the unit for work would be the same as energy. Another thing I want to mention here, number 70 here. So it's talking about an angle, and it says that the angle is below the horizontal. That doesn't matter as much. If it's there, if we have basically we're traveling in this direction. If your angle is above the horizontal or below the horizontal, it doesn't really matter because the x component of both of those is going to be completely to the right. So you don't have to think like, oh, it's above the horizontal or below. Both of these are making it go in the to the positive direction there. Whereas if you had it in the opposite direction, where if it's moving over here in V and you have a force that's there and a force that's there, both of these would cause a negative work to be done because it's an angle that is on the other side of the velocity. So you would calculate, how you would calculate the one right here with 21 degrees would be the same way if you calculate it with if it's above the horizontal or below the horizontal. Last thing I want to mention here is 71. You're having to calculate the work, and so it says you pick up a 3.4 kilogram can of paint from the ground and lift it to a height of 1.8 meters. So once again, you'd have mass times 9.81 times 1.8, and you get work. And they're actually, how much work do you do on the can of paint? So we have to make sure we're calculating whether or not it's positive, negative, or zero. And so a real kind of quick way to just think about this is, let me just calculate how much work that is. So it's 3.4 times 9.81 times 1.8. That gives us an energy of, try to move this around here, energy of approximately 60, we'll just round it out, 60 joules. So we have this can of paint, and you're lifting it up. So think about it. The velocity is upward, and you're applying an upward force on it. So it is 60 joules, but you want to make sure that you indicate that it is positive 60 joules because you're putting energy into the system. Part B then says you hold, so I'm going to move over here, you hold the can stationary for half a minute waiting for a friend on a ladder to take it. How much work do you do during this time? Well, let's see here. It's now at this height. You're still imparting a force on there to keep it up. However, you're not moving at all. Here you have a change in distance. The distance change is 0. So if you have force, or work equals force times distance, and this is 0, then the work is 0. So even though you're imparting force on it, if you're not moving it, if you're not changing its position, then you're not doing any work on it. And then the last part says over here, it says, your friend decides not to use the paint, so you lower it back to the ground. How much work do you do on the can as you lower it? So you can't just say 60 joules, 0, 60 joules, because in the last case here, the can of paint is being lowered. You're still applying a force upward here in order for it to not fall, but now the direction of travel is this way. So because these are in opposite directions, the work would be 60 joules, and then you'd have to mark that it is a negative work. Negative work because it's removing energy from the system. Here, we're giving it potential energy. We're not changing the energy here, so there's no work being done. Here, we're lowering the amount of energy we have, so you're losing 60 joules of energy. It's being dissipated outward. So that wraps up what I wanted to talk. We basically went through almost all of them. But if you could watch the video, or you're watching the video already, and then fill this out and make sure you show your work. And then upon your return, or we may set something up that you can submit a picture, that would be very helpful. So look on out for a place to submit this when you are done. And if you don't have, you should have a book with you, but if you don't, you can just request, you can ask me and I can try to take some pictures of this. Actually, you have a video, never mind. So I'll go ahead and end it, and thanks a lot.